Right, welcome back, everybody. Let's take a look at a final example. This example is a little bit different. Before we continue, let's just uh, recall, what is the goodness of fit test checking? So it should make a lot of sense for what a goodness of fit test is checking. Remember that a fit test is checking the level of disagreement, or maybe I should say agreement or disagreement, between a claim distribution and the data slash sample. So how do we say that? And between the distribution of the actual data. In essence, just the sample. So this is important for us to remember because we are the ones that need to come up with the claim distribution some of the time. So here's the example where the parameter is known, and then you just go ahead and continue the procedure exactly as before. So the example reads, a supervisor at Fast Track Professional Temporary Service suspects that her employees are more likely to call in sick on Mondays and on Fridays than on other days of the week. And if you work, I guess that makes sense, right? You maybe want a longer weekend, so you can call off on Friday, and then that'll give you a slightly longer weekend. So if that is true, we have an idea of what we expect to see, but it's really hard to test this. So what we're going to do is we're going to go ahead and just collect some data. And then we're going to go ahead and try and see how we can come up with an expected distribution. Okay, so we're going to go ahead and test the claim. This supervisor collects data. And here are the results of that sample. So in other words, we have the distribution of our sample. We don't have the expected distribution yet. Go ahead and add these up. So let's see, 7, 13, 20, 31, 38, so 47. So we looked at 47 individuals who called out. I guess this has to be done random somehow. And the question is, from this, does it appear that the absentees are not equally distributed across the 5 days? And you can see why this is very different. The fact that they say not equally distributed, it means that we know the probability of success for each one. So this is essentially that whole die rolling or selecting a suit example that we did at the very introduction of the unit. There are 5 days, so there are 5 options. If those days are equally distributed, then that means that the probability of any day being selected, so the probability of day I, it should be the same as any other day. So it should be 1 out of 5. So notice that the fact that they said equally distributed means that I can find the probability. I am the one that finds the probability. So because of that equally likely hypothesis, we have that the P sub I, the probability of calling out sick on I, is 1 over 5. Therefore, the null hypothesis is going to be, is it true that for day 1, that has a probability of success of 1 out of 5? Is it also true that for P2, you have a probability of success of 1 over 5? And so on. So that's how we could write it, or you could write it differently. So let's try and write this in words also. You could either write it like this. There's a little bit mathematical. Or we could write the hypothesis as the absentees are not, or sorry, we're going to assume that they are, and then the alternative is that they're not. Absentees are equally distributed across the 5 days. The alternative is that they are not. So again, not all the proportions of success are going to be 1/5. All right, now for this one, I actually do recommend that you do this by hand just to emphasize what it is that we're doing. So remember that the next step is to check the requirements. Now for us, I want us to do it by hand. Whenever you have equally likely, it means that all the expectations are going to be the same. So you expect the same number of people calling out sick on Monday, then on Tuesday, then on Thursday, and so on. So equally likely indicates that the expected count is going to be the same. So it'll be P times N. Or I think maybe I wrote it backwards earlier, N times P. Where P is only a single P, because remember what we're saying? The probability is the same no matter what group you're talking about. So here, if I looked at 47 individuals as my sample, then I can go ahead and multiply that by 1/5. And that gives me 9.4. So let's take a look at what this gives me then. This now says that your data is so let's look at observed. And then let's look at expected. So for expected, it's always going to be 9.4. But for observed, I'm going to put the actual numbers that I observed. So 13, 11, 7, 7, and 9. Okay, so that is going to be my data set. Now, notice that this actually does agree quite a bit, 9 and 9.4, 7 and 9.4. So that there's some disagreement there. 13 and 9.4, there's gap of about 4. So again, more disagreement. So anyway, let's go ahead and complete our test. From here on out, I'm going to go ahead and sketch my, or let's check if the EIs are all 9.4, then you can see that the EIs are all greater than 1. And no EIs are less than 5. So both of my requirements are met right away. And I can go ahead and proceed to sketch my chi-square distribution. All right, now degrees of freedom, there were 5 days, so degrees of freedom is 4. So go ahead and find the chi-squared value, as well as your chi-square stat and p-value. All right, so your critical value is just 9.48. I guess 8. For your chi-square stat, you can actually type this into StatCrunch. Like this. Now, you could type in 9.4 for each one. And then it's the same thing as the test that we had before. So there's the expected. So again, stats, goodness of fit, chi-squared. And lo and behold, we get our chi-squared and the p-value. Now, there is another way of doing this. Whenever you see equally likely, because the expected counts will be the same, StatCrunch can do that. So we can just type in the data. In other words, the observed data, 9, 7, 7, 11, and 13. And then we could go to stats, goodness of fit, select the observed, and then the expected, select all cells in equal proportion. And notice that StatCrunch has done the same thing we did. They're just seeing how long is this list? Those are the number of categories. We're going to do 1 over K, add up all the entries, and then compute the expected count. And it's going to be the same for each category. Again, we get the same thing. All right, so 2.85, but you can see that that is in the non-critical region. So therefore, we're going to fail to reject the null hypothesis. So unfortunately, we have insufficient evidence to say that the absentees are not equally distributed across the 5 days. So again, this is the statistical procedure. Number-wise, we might get a sense, like if we did not have a statistical procedure, that there does seem to be more people absent on Friday, but the rest of the days, there does seem to be agreement. And so again, that one difference is not enough given the level of agreement in all these other days. All right, so that was our last test. And again, that happens whenever you have equally likely. You're usually only going to be given the observed data. All right, thanks for joining me. That is it for the examples.